In our last lesson, we proved Fermat's theorem in the n equals to 4 case, and we saw two different proofs of that result. One proof followed de Bézi's argument by using Fermat's right triangle theorem to deduce the n equals to 4 case of Fermat's theorem. Of course, we could make the argument that Fermat did in fact have a proof of the n equals to 4 case, since as we saw, proving Fermat's theorem in the n equals to 4 case by means of the right triangle theorem is an easy consequence once we use Diophantus's right triangle theorem. But of course, Fermat never, at least no writing of Fermat has survived to suggest that he wrote down a proof. And taking Fermat at face value, as we have seen throughout this term, is questionable whether he had a proof, even though he claimed in his writings to other mathematicians to have proven it. But he also claimed to have proven the n equals to 3 case in his writings, and as we saw in our discussion, that result would take Euler, it would not come until a century later, and even then, Euler made a fundamental flaw in his original argument, which he would later fix almost 20 years later. And so, with the second proof, this brings us to Euler. We're now a century after Fermat wrote his original marginal note, and Euler gave a new proof of the n equals to 4 case. And it did not require the right triangle theorem, and both proofs are rather similar. And when you do prove Fermat's right triangle theorem, you'll see that many of the elements that are in that proof are also in the proof that we did for the n equals to 4 case of Fermat's theorem via Euler's approach. But what happened after? So at the end of our last lesson, we finished off with Euler and the n equals to 3 case, and how in doing the n equals to 3 case, he stumbled upon the roots of unity, and ideas that would later lead Eisenstein to prove cubic and quartic reciprocity. But Eisenstein's work built on other mathematicians who had followed that thread that Euler began in his investigation. But what was the next breakthrough when it came to Fermat's theorem? It would not come for almost 50 years after Euler fixed the n equals to 3 case. And that is in 1825 if we strictly care about the proofs of actual cases. And so this is what we're going to do now. Just go through the timeline, talk about the main statements, the arguments that were proven pertaining to Fermat's theorem by cases. And so n equals to 5, 1825, Dirichlet and Legendre. And they both, actually, to be precise, they both proved this independently the same year, and we will talk about in just a moment how they were able to both achieve that monumental breakthrough almost at the same time. So 7 years after the n equals to 5 case, Dirichlet proved the n equals to 14 case. But we also saw at the end of our last lesson that because the n equals to 4 case is true, it suffices to prove Fermat's theorem for all the exponents p. Well, Dirichlet tried to do the n equals 7 case, got stuck, and by going to the n equals to 14 case, working over 14 fruits of unity, there was more structure that he could invoke, and he used that to prove the n equals to 4 case of Fermat's theorem. Gabriel Lemay, 7 years later, strengthened Dirichlet's argument and was able to remove that restriction to working over the 14 fruits of unity, and he was able to succeed in proving the n equals to 7 case of Fermat's theorem, thereby making Lemay one of the frontrunners in term at the time for the proofs pertaining to Fermat's theorem, and he also had given a new proof of the n equals to 5 case. Lemay in 1847 made a fool of himself, however, because he went to the Paris Academy of Science and gave a lecture where he proved Fermat's theorem, and we'll talk about this in further detail in our next lesson, but it did lead to a lot of drama because his proof was incorrect. It was wrong, fundamentally wrong, and at its core was this notion of unique factorization. So we'll discuss that in further detail in our next lesson. But while Lemay's proof was wrong overall, it did hold true for primes less than or equal to 19. But that same year, Ernst Kummer was also arguing the same exact strategy that Lemay had done, but Kummer realized the subtlety that Lemay did not. And so he created a machinery so that he could prove Fermat's theorem in a special case, what he called regular primes. And it's this work that laid the foundations to not just ring theory, but algebraic number theory as well. And we'll talk about this in further detail in our next lesson. And so this is Kummer's work from 1847. And while he proved it for regular primes, we actually do not know even today if there are infinitely many regular primes. But we do know from Johann Jensen's work in 1915 that there are infinitely many irregular primes. And so that's where things were up to 1915. Kummer's work on regular primes meant that one just had to prove Fermat's theorem for the irregular primes, but since there were still infinitely many, we were just as close to proving Fermat's theorem as we were at the time of Euler. In the sense, we're still infinitely far away from proving it. But a good chunk of work had already been done. Regular primes, while we don't know that there are infinitely many, there is good numerical evidence and theoretical evidence to say that yes, there are. And actually, the conjectures are that there should be roughly 60-ish% of all odd primes should be regular, but no proof exists of that claim. Now let's go ahead, fast forward 40 years to 1955, and this is completely unrelated at the time, but Taniyama and Shimura, Japanese mathematicians, were investigating some parallels between the theory of elliptic curves and the theory of modular forms, two topics that we will investigate next week. And they were able to make a connection that essentially there seems to be a correspondence between elliptic curves, which are algebraic, and modular forms, which are analytic. These are functions. And so we'll see these in further detail in our next lesson, our lesson on Monday. And they made a conjecture, which we now call the Taniyama-Shimura, well, it's now proven, but at the time, it was called the Taniyama-Shimura conjecture, also named Taniyama-Shimura-Weil conjecture after André Weil, who also contributed to the conjecture itself. Also, today it's known as the modularity conjecture. So those are various names in the literature for the original conjecture of Taniyama-Shimura. But the connection to Fermat's theorem would not come until 1982. So Gerhard Frey, in 1982, published a paper that gave a roadmap of how Fermat's theorem could be proven. And this was done by Frey building upon a conjecture of Lucien Spiro the year before that made him realize that if Fermat's theorem is false, one could then contradict this conjecture of Taniyama and Shimura, the modularity conjecture. And so, as a consequence, Frey showed that if the modularity conjecture is true, then Fermat's theorem itself must also be true. In 1986, Ken Rivett, building on work of Sir, was able to show that Gerhard Frey's roadmap to proving Fermat's theorem is valid. Rivett showed that if the modularity conjecture is true, then Fermat's theorem would also be true. And finally, the modularity conjecture was proven in 1994 by Andrew Wiles and Richard Trader, thereby settling this 357-year-old problem. And while this roadmap existed, a year after Wiles and Taylor's proof, Noam Elkies was able to show that one can get Fermat's theorem directly from the work that Wiles and Taylor had done without invoking the roadmap that Gerhard Frey had set up. And so this is the general idea for how this all connects with the theory of Fermat's theorem. And we have all these various threads. And what we are going to be doing to finish off the term is going through this timeline and discussing, while waving our hands, how Fermat's theorem was proven. And so we have to discuss what are elliptic curves, what are modular forms. And so that's one of the tasks that we will be doing in the next 3 lessons, is building up this roadmap. But now, for today, what we want to do is talk about something that happened in between here. Because if we see, up to 1770, the work on Fermat's theorem was quite sparse. We had hardly any achievements being done in over a century. And we're now almost 2 centuries by 1825. And then over a span of a few decades, a lot happens. And so there is a monumental work that happened right before 1825, which allowed Dirichlet and Legendre to both independently prove the n equals 5 case of Fermat's theorem. So to better understand the context for what we are about to discuss of what happened right before 1825, let us go to 1808. And so Pierre Simon Laplace, whom some of you may have already encountered in other math courses, introduced Napoleon to Ernst Shanley, a German physicist. And so Laplace at the time was Napoleon's Minister of the Interior. And Shanley gave a demonstration to Napoleon of an experiment which got Napoleon's attention to the point that Laplace wrote down that Napoleon was struck by the impact which the discovery of a rigorous theory capable of explaining all the phenomena revealed by these experiments, the experiments that Shanley had shown him, would have on the advancements of physics and analysis. So what was this experiment? Well, let's see a demonstration. So this here is a modern demonstration of what Shanley showed Napoleon in 1808. And so we are putting sand on a plate. And so here now it's vibrating. We have a frequency being applied of 345 Hertz. And now observe what happens as the frequency is changed. And so you can find various demonstrations of this on YouTube if you're interested. But this was the experiment that caught Napoleon's attention. In fact, Napoleon recommended that an extraordinary prize be commissioned to whoever could explain the mystery that was happening in Shanley's experiment. And the following year, the Paris Academy of Science did just that. And so here is the excerpt from April 1809, which announced this extraordinary prize, or how it's in French, the Prix Extraordinaire. His Majesty the Emperor and King, being struck by the impact that the discovery of a rigorous theory explaining all phenomena rendered sensible by these experiments would have on the progress of physics and analysis, desires that the class make this the subject of a prize. The class has thus proposed for the subject of the prize the development of a mathematical theory of the vibration of elastic surfaces and a comparison of this theory with experiments. And so this was dated 1809, and 2 years later, 1811, a submission was entered, which, while incorrect, did catch the attention of the judges. And so there was a submission by a person who signed it off as Monsieur Leblanc. Monsieur Leblanc's submitted work was incorrect, but Lagrange, who was one of the judges, realized that the solution was ingenious, and while incorrect, he was able to fix some special cases to show that it did have merit for giving a general theory for how this phenomena occurs. And Lagrange's work was unable to give a solution, and so years passed, and finally, a correct solution was announced once more by Monsieur Leblanc in 1816. And the solution came in the form of a partial differential equation. And so here's the partial differential equation which answers Shanley's experiment. And so we have this constant k squared, and then we have these partial derivatives. But the way that this is being interpreted is that we're looking at a function z is equal to f of x comma y comma t, where here the function is giving us the amplitude at the point on the a point x comma y on the surface at a given time t. So who is Monsieur Leblanc? Monsieur Leblanc is the pseudonym used by Sophie Germain. She was born to an aristocratic family in 1776. When she was 13, the Bastille fell, and she retreated to her father's library to escape the mayhem that was going around her with the French Revolution. She taught herself Latin and Greek so that she could read the original works of Newton and Euler and other prominent mathematicians of the 17th and 18th century. But her parents did not take kindly with her fascination of mathematics and philosophy. They did not deem it appropriate for a woman to consider these academic pursuits, and they went as far as to not provide her warm clothing or fire in her bedroom so that she could keep studying. But she persevered. She wrapped herself in blankets, continued to study at night with the only source of light being a candle. Mathematician Lynn Olson describes Sophie's parents would find her asleep at her desk in the morning, the ink frozen in the inkhorn and her slate covered with calculations. When she was 18, she began to correspond with contemporary mathematicians, one of whom we've already covered in our course, Lagrange. During her time studying, she was able to acquire Lagrange's lecture notes, and she used the pseudonym Monsieur Leblanc for the first time to correspond with Lagrange, who was so impressed with her mathematical brilliance that he requested a meeting with her, which forced Germain to reveal her identity to him, and Lagrange became her mentor and collaborators for the remainder of his life. And she continued to correspond with other mathematicians, including Gauss, under the pseudonym Monsieur Leblanc. During the Napoleonic era, when the Napoleonic troops invaded Germany, she was able to contact a family friend to ensure the safety of Gauss during the invasion. And so the following is the quote of her family friend and Gauss responding. And Gauss during this time, even though they had corresponded, Gauss did not know of Sophie Germain, as in all their correspondences, she signed everything under Monsieur Leblanc. Monsieur Pernety, Sophie Germain's family friend, who she tasked with ensuring Gauss's safety, wrote back to Sophie to inform her that he had just arrived in town and bruised myself with your errand. I have asked several persons for the address of Gauss, at whose residence I was to gather some news on your and Sophie Germain's behalf. Monsieur Gauss replied that he did not have the honor of knowing Mademoiselle Germain. After I had spoken of the different points contained in the order, he seemed a little confused and asked me to convey his thanks for your consideration on his behalf. Upon receipt of Monsieur Pernety's letter, Germain wrote to Gauss on February 20, 1807, to clear up any confusion that had arisen of the whole encounter. In the process, she revealed herself to be Monsieur Leblanc, the person who had been corresponding with Gauss now for several years. And the following is an excerpt of the letter that Germain wrote to Gauss, and at the end, she mentions how she has always admired with new pleasure the linkages between truths exposed in your book. The book she references is Discussiones Arithmeticae, the book that contained the first proof of the law of quadratic reciprocity, as well as the foundations of modular arithmetic. It was the book that introduced the mathematics community to modular arithmetic, and as we have seen throughout our course, those tools have played a premier role in allowing us to prove the things that we have proven throughout this term. Gauss responded a few weeks later with the following letter. So go ahead and you can read through. To her relief, Gauss accepted her for who she was, and he writes, Monsieur Leblanc metamorphosed into this celebrated person, yielding a copy so brilliant it is hard to believe. The taste for the abstract sciences in general, and above all, for the mysteries of numbers is very rare. This is not surprising, since the charms of this sublime science in all their beauty reveal themselves only to those who have the courage to fathom them. But when a woman, because of her sex, our customs and prejudices, encounters infinitely more obstacles than men in familiarizing herself with their knotty problems, yet overcomes these fetters and penetrates that which is most hidden, she doubtless has the most noble courage, extraordinary talent, and superior genius. Nothing could prove me in a more flattering and less equivocal way than the attractions of that science which have added so much joy to my life are not chimerical than the favor with which you have honored it. And Gauss would go on to be a champion for Germain, eventually getting her an honorary doctorate from Göttingen in 1830. But as of this writing, this was 1807, the work that Germain is known for had not come yet. And we just saw Chanlay's experiment, which drew Napoleon's attention to create the extraordinary prize. But that would come several years later. And so let us go ahead and turn to that now. In 1816, Germain won the Prix Extraordinaire. She solved the question that the Paris Academy of Science had posed at the direction of Napoleon through her partial differential equation. And yet, her solution was not made public. The only ones to read it were the judges, one of which is Poisson, who today is synonymous with at least the foundations of the theory of elastic materials. His work built upon the work that Germain had done and was not given proper credit. Germain did publish her work at her own expense so that it could be made public. And while she won the Prix Extraordinaire, she was not allowed to claim the prize in person, since women were not allowed at the Paris Academy of Science. Specifically, the only women allowed were the wives of the members. And so while she won the prize, she was snubbed from being able to claim it in person. But that did not deter her. After the Prix Extraordinaire was won, the Paris Academy of Science made another extraordinary prize, this time for Fermat's last theorem. And mathematicians within the Paris Academy of Science corresponded with mathematicians abroad and within France to get them interested to pursue a proof of Fermat's theorem. One of the first that was reached to was Gauss himself, to which he responded on March 12, 1816. I am very much obliged for your news concerning the Paris Prize, but I confess that Fermat's theorem as an isolated proposition has very little interest for me, because I could easily lay down a multitude of such propositions which one could neither prove nor dispose of. And Gauss had already written in 1807 on the matter of Fermat and his opinion of Fermat. He wrote, "Higher arithmetic has this special feature, that many of its most brilliant theorems may be easily discovered by induction, while any proof can be only obtained with the utmost difficulty. Thus it was one of the great merits of Euler to have proved several of Fermat's theorems, which he obtained, it appears, by induction." And here induction is not how we use induction today, but more by making examples and deducing a pattern that should hold in general, but not having a rigorous proof. However, Sophie Germain was not deterred by the prospect of Fermat's theorem. To her, there is a new prize, and she went and read through the literature to see everything that had already been done pertaining Fermat's last theorem so she could tackle it. And from 1816 through 1819, she devoted herself to only read the mathematics literature as it pertained to Fermat's last theorem, learning the works of Euler that we have covered in our course, getting as much as she could so that she would be able to tackle this long-standing question. And in 1819, she made a breakthrough. She realized that if we focus on the expansion that we had been looking at previously, the proof that Euler had done in the n equals to 3 case could be expanded into a general program. She was able to see from the proof that Euler had done that Fermat's last theorem should be broken into 2 cases. And these were the 2 cases that she deduced. Case 1, let P be an odd prime. There are no solutions xyz, with xyz being not equal to 0 to the Diophantine equation x to the p plus y to the p equals z to the p, such that p does not divide one of x, y, or z. And then the second case is the remaining situation, which is now there are no solutions x, y, z non-zero, such that p divides one of x, y, or z. And so this was how Sophie Germain envisioned Fermat's last theorem to be proven. Break it up into 2 cases and only work 1 case at a time, and create a method for doing this for as arbitrarily many exponents as possible. And that's what she devoted herself to do for the next 4 years, eventually succeeding. She proved Fermat's last theorem in the case 1 situation for primes all the way to less than 100. And in the years that followed, she extended her work with collaborators to odd primes less than 1,000. And at the core of it was her theorem on Fermat's last theorem case 1 for auxiliary primes. And this was done in 1823. And that is the purpose of today's lesson, is to prove Germain's theorem of 1823. With what she did, mathematicians that came after only had to worry about proving case 2. Since Germain's work had established Fermat's last theorem in the case 1 situation for primes all the way through 1,000. And therefore, 2 years after, the n equals 5 case was done by Legendre and Dirichlet, building on her work. And the mathematicians that came in the years after also built on the techniques and methods that she had done and saw patterns in the same way that she saw patterns in what Euler had done to lead to a more general program for Fermat's last theorem. So let us go ahead and start building towards Germain's theorem. So our first definition is that of an auxiliary prime. So we're going to go ahead and fix P to be a prime number. And an auxiliary prime for P is a prime Q that satisfies the following 2 conditions. There are no consecutive non-zero p power residues modulo Q, and the number P is not a p power residue modulo Q. To best see this definition in action, let us consider some examples. So let us get started by considering the case when we don't have an auxiliary prime. So the claim is the prime 5 is not an auxiliary prime for 3. So in other words, we have that the auxiliary prime in question that we want to show is not the case is 5, that's our Q, and P is equal to 3. And so we want to consider the third power residue. So that is, what are those perfect those perfect cubes modulo 5? And so we're going to do a table. We're going to consider, as we go over the integers modulo 5, and so we're going to be working in Zmod in the integers modulo 5, and we're going to be considering x cubed. And so we're going to do, since we're working modulo 5, we only have to consider the non-zero ones, 1, 2, 3, and 4. Those are the non-zero. And we're going to consider each of these cubed. So 1 cubed, we get back 1. 2 cubed, we're going to get back 8, which is 3. We get 3 cubed, 27, that is going to be 2. 4 cubed, we are going to get 64, which is going to be 4 modulo 5. So we have this here. So consequently, we have that 1, 2, 3, and 4 are third power residues, or cubic residues, modulo 5, but they are consecutive. 1, 2, 3, 4. All of these are consecutive. Which are consecutive, and so condition 1 fails. And that's what we wanted to do. So that's one way of seeing that 5 is not an auxiliary prime for 3. We see that this here fails. But we could also do the following. We also have the second condition, which fails in this case too. We have that the number p, if it's not a p power residue modulo q, that must be a condition to have an auxiliary prime. But here we have that 3 is in fact a cubic residue modulo 5. So alternatively, we have that 3 is a third power residue modulo 5, and so 2 fails. And so that's the first example. So let us go ahead and consider another one. We now want to show that 11 is an auxiliary prime for 5. So we go ahead, as we did with the last example, we can go ahead and consider x to the 5th modulo 11, where x is a non-zero element or congruence class of the integers modulo 11. And so we can go through and do 1 to the 5th, that's 1, 2 to the 5th is going to be congruent to 10 modulo 11, and we continue. And what we see is that the 5th power residues are just 1 and 10. These are not consecutive. So the 5th power residues modulo 11 are 1 and 10, and thus we have that conditions 1 and 2 are satisfied. And so 11 is an auxiliary prime for 5. Let's do one more example. 23 is an auxiliary prime for 11. We go ahead, make our table, but now we have to consider the non-zero elements modulo 23. So now we're going all the way from 1 through 22, and we are considering x to the 11 mod 23. So we can go through, and what we see is that the 11th power residues modulo 23 are just going to be 1 and 22. In this case, we don't have, none of these, 1 and 22 are not consecutive, so 1 of the definition is satisfied. And we also have that 11 is not appearing in here, so 11 is not a p power residue. And so we do have that 23 is an auxiliary prime for 11. Most authors incorrectly state Germain's theorem in a weaker form because the definition of an auxiliary prime is rather technical, and as we see, we need the language of residues modulo a prime q. And so they usually will state Germain's theorem for what are known as Germain primes. And so we say that a prime p is a Germain prime if 2p plus 1 is prime. And so we have that the first Germain primes that are less than 1,000 is the following list. And so we have that 2 is a Germain prime, since if we take 2 times 2 plus 1, we get 5. 3 is a Germain prime, because if we take 2 times 3, 6, plus 1, 7, then we have 7 is prime, so 3 is a Germain prime. Similarly with 5, we get 2 times 5 plus 1 is 11, so 5 is a Germain prime. However, with 7, we have 2 times 7 plus 1, which is 15, not prime. So 7 is not a Germain prime. And we can go through and continue in this process and verify that each of these will be a Germain prime. Interestingly enough, today we still don't know if there are infinitely many Germain primes, although they are heavily used in cryptography. And the reason why Germain's theorem is usually said in the language of a Germain prime rather than the technical definition of an auxiliary prime is that we have that if P is a Germain prime, then 2P plus 1 is an auxiliary prime for P. Let us go ahead and prove this. So here we are. We're going to be using this lemma, which we did back when we proved Wilson's theorem. If P is a prime and x bar is its own multiplicative inverse in the integers modulo P, then we have x bar is equal to 1 bar, or x bar is equal to P minus 1 bar, or just negative 1 bar. So let's go ahead and prove this. Well, by this I mean the lemma. So we want to prove that 2P plus 1 is an auxiliary prime for P. What we are going to do is start off with the following claim. So we claim that x to the P is congruent to plus or minus 1 modulo 2P plus 1 for each non-zero, or for each x in the naturals that is relatively prime to 2P plus 1. Now since 2P plus 1 is prime by assumption, so we have that P is a Germain prime, so that means that 2P plus 1 is prime. So since 2P plus 1 is prime, by assumption, we have by Fermat's little theorem that x to the 2P plus 1, since that's prime, minus 1, which is equal to x to the 2P, is congruent to 1 modulo 2P plus 1. But that's the same as saying x to the P times x to the P is congruent to 1 mod 2P plus 1. Therefore, x to the P is its own multiplicative inverse. In the integers modulo 2P plus 1. And now we use dilemma 186. We have that x to the P is congruent to 1 or negative 1 modulo 2P plus 1 until we got the claim, because now we have what we wanted. We have x to the P is congruent to plus or minus 1 modulo 2P plus 1. But we are done. So in particular, since 1 and negative 1 are not consecutive, so in particular there are no consecutive P power residues modulo 2P plus 1, and we also have that P is not a P power residue modulo 2P plus 1. And so we can conclude that 2P plus 1 is an auxiliary prime for P. And we're done. We have now shown the claim. And that's the great thing about Germain primes, is that they satisfy this technical condition to be an auxiliary prime. And so this is a special case when considering Germain's theorem. In order to prove Germain's theorem, we need the following lemma. So let's go ahead and distribute over. We're going to go ahead and distribute this x, multiply it over, and this y, multiply it over. You can verify that this expression here is the same as this sum. As this sum. That sum right here is equal to this expression here. So what we are going to show is that upon expanding this out, this in fact is x to the p plus y to the p. And let me go ahead and call this s. So prove. So let's go ahead and observe that s is equal to x to the p minus x to the p minus 1 times y, and then this just continues, minus x squared y to the p minus 2 plus a y to the p minus 1. So that's only coming from multiplying the x over. Now let's go ahead and multiply the y. Then we have a y x to the p minus 1 minus x to the p minus 2 y squared. And we're going to have a minus x y to the p minus 1 plus y to the p. So we got this here. But the key thing is that we now have cancellation. We're going to have a cancellation here. We have a negative x to the p minus 1 times y, which will cancel with this. The next term that's following up over here is going to be x to the p minus 2 times a y squared, which is going to cancel off with this term here. So we're going to have that cancellation. And this is going to continue. We're going to have xy to the p minus 1 cancel off with our xy to the p minus 1, which I just realized I made a typo. There should be an x here since we were distributing the x over to each of these. And so now we have the cancellation that we wanted there. And so each of these will cancel. And so what is going to be left over after the cancellation is just simply x to the p plus y to the p. And so we got that this equality holds. So let's go ahead and prove Germain's theorem. So if p is a not prime, and if we have that there exists an auxiliary prime for p, then case 1 of Fermat's theorem is true for the exponent p. So here's the proof. We're going to go ahead and go by contradiction. So by way of contradiction, suppose that case 1 of Fermat's theorem is false for some odd prime p. Then we can find natural numbers x, y, and z such that x to the p plus y to the p is equal to z to the p, with p not dividing x, y, or z, or just the whole product. So p does not divide the product of x, y, and z. Now we can go ahead and choose x, y, and z to be relatively prime. So moreover, if D is equal to the GCD of x and y, then we have that x over D to the P plus y over P D to the P is equal to Z over D to the P, and thus the GCD of x over D, y over D is equal to 1. So in particular, we may assume, after relabeling, that x, y, and z are relatively prime. Now we consider the previous lemma. And so by lemma 1.25.7, we end up getting the following factorization: z to the p, which is going to equal to x to the p plus y to the p. That is going to be x plus y, and then we're going to have the product x to the p minus 1 minus x to the p minus 2 times y, and then we're going to just continue on in this way as we had in the lemma. X to the y to the p minus 2, and then finally y to the p minus 1. And we're going to claim that x plus y and x to the p minus 1, the whole thing, is that these are relatively prime. So x plus y and x to the p minus 1, x to the p minus 2, y are relatively prime. So we're going to do another contradiction assumption. We show the claim by contradiction. So let us go ahead and suppose that they are now relatively prime. Then there is some prime number let's call that prime number n, which divides the two quantities. So in particular, since it divides them, we have that x plus y is congruent to 0 mod n, which tells us that x must be congruent to negative y mod n. But we are working modulo n. So what if we go ahead and substitute? And actually, for the substitution, just to make things nicer, let's go ahead and switch this around to y congruent to minus x mod n. So now we're going to go ahead and consider this modulo n. So keep in mind, by assumption, this is congruent to 0 mod n. And what we are going to do is substitute y is equal to negative x into this. So then we have that x to the p minus 1 minus x to the p minus 2y all the way to p minus 2 plus y to the p minus 1. This is going to be congruent, since y is congruent to negative x. This will be x to the p minus 1, and then minus x to the p minus 2 times y, which is now negative x, So that's going to give us a plus x to the p minus 1 right there. Then we consider the next term. Over here, we're going to have a x to the p minus 3, a plus x to the p minus 3 times y squared. Y squared is now going to be negative x quantity squared. That's going to give us back x squared modulo n. And so upon multiplying, we're just going to get back x to the p minus 1 again. And we're going to continue along these lines and just continue going forward. We finally come down over here. We have now p minus 2, but p is odd. So p minus 2 is odd. So we have negative x to the p minus 2. That's going to give us back a negative x to the p minus 2 times x. That will give us x to the p minus 1 times, the negative will become positive. So we have another x to the p minus 1. And finally, y to the p minus 1. P minus 1 is even. So putting a negative x, we just get back x to the p minus 1. But this has, in here, p terms. Oh, and this is modulo n. And so what we have is that this is congruent to p times x to the p minus 1 modulo n. But here's the thing. We started this argument by assuming that n is prime, and specifically n is a prime that divides both x plus y and this quantity. So this quantity that we were just looking at is divisible by n. So this is also congruent to 0 mod n. So consequently, we have that n divides p to the p times x to the p minus 1. So we have n divides x to the p times x to the p minus 1. Now, since n is prime, we have by Euclid's lemma that n divides p, or n divides x to the p minus 1. Now, if n divides x to the p minus 1, then of course n has to divide x. And thus, if we come back, we said x plus y was congruent to 0 mod n. So if n divides x, which we have the negative x is congruent to y, then n also divides y. And so we have x divides y. But this is a contradiction. So this contradicts that x and y are relatively prime. Because after our relabeling, we were able to assume that x, y, and z are relatively prime. So we are able to eliminate this situation. And so what we end up getting is that n has to divide p. So then, n divides p, but n is prime and p is prime, and so we get that n must be equal to p. So we get this here. But now n divides x plus y, and so it has to divide z to the p. So in particular, p divides z to the p, which is another contradiction. So p divides z to the p, which implies that p divides z, which contradicts our assumption. And so now this shows the claim. So we have now established that x plus y and the quantity x to the p minus 1 all the way to y to the p minus 1, that these two are relatively prime. And so we have now shown the claim, so we can go ahead and say that these are in fact relatively prime. So now we're going to use the following lemma. We have from lemma 124.1 that if we have natural numbers z and n such that z to the n is equal to d times z, where d and e are relatively prime natural numbers, then we have that d and e are both perfect nth powers. And so we have now that x plus y and x to the p minus 1 minus x to the p minus 2 times y all the way through y to the p minus 1, these are relatively prime. But they are equal to z to the p, since we have that z to the p is equal to x to the p plus y to the p, which is equal to this. Since they are relatively prime, this has to be a perfect p-th power, and so must this. So in particular, we get the following. So by lemma, (124.1), there exists natural numbers a and r such that x plus y is equal to a to the p, and x to the p minus 1 minus x to the p minus 2y and this here is equal to r to the p. And now what we are going to consider are the following. So we're going to consider the following. We're going to have x to the p. So we know that x to the p is z to the p minus y to the p. But we also have that y to the p is equal to z to the p minus x to the p. And so we can go ahead and factor these out in the same way that we did with z to the p, where we got x plus y times this. And if we do a factorization here, we are going to get the following. So we have the two factorizations over here. If we do the same exact argument that we just did, we go about contradiction by, we claim that each of these two factors, z minus y and this factor here, and similarly z minus x and this factor here, we go through and claim that they are relatively prime, and to prove it we go by contradiction, run through the same exact argument we just did, we will prove that they are relatively prime. So the same argument than above shows that the two factors of z to the p minus y to the p and z to the p minus x to the p are relatively prime. And as a consequence, we can then apply lemma 124.1 once more. So by lemma 124.1, we have the existence of natural numbers b, c, s, and t, such that we get z minus y is equal to b to the p. We have z minus x is equal to c to the p. And then we have the second factors. We're going to have z to the p minus 1. And so we got these here. So we have s to the p is equal to this factor, and t to the p is equal to this factor. But we still have not used the fact that we are given that q is an auxiliary prime for p. And so let's go ahead and use that assumption now. So next, let q be an auxiliary prime, and by assumption this exists. For p, and we're going to do the following deduction. So if we consider the Fermat equation x to the p plus y to the p equals z to the p, and bring it over, we have that x to the p plus y to the p minus z to the p is equal to 0. And this implies that x to the p plus y to the p minus z to the p is congruent to 0 mod q. In fact, since it's equal to 0, it will be congruent to 0 any modulo any natural number m that we choose. And so this here is just, there's nothing happening here from this, but we are going to use this equation to our advantage. Because what we are going to claim now is that q divides x, y, or z. So now we claim that q divides x, y, or z. And we are going to approach this in the same manner that we did the previous claim. We're going to do a contradiction argument. So towards a contradiction, suppose that q does not divide x, y, and z. So if q does not divide x, y, z, the product, then it can't divide x, y, or z. But if q does not divide x, that tells us that x is a multiplicative residue modulo q. So then x is a multiplicative residue modulo q. So there exists some natural number w such that if we take w times x, we get back that this is congruent to 1 mod q. But now we go ahead and multiply this equation here by w to the p, we get the following. So we have that x to the p plus y to the p minus z to the p congruent to 0 mod q. After multiplying by w to the p, we're going to have x times w to the p, that's going to be 1. So we're going to get a 1, but then we're going to have a plus wy to the p minus a wz to the p is congruent to 0 mod q. So we got this here. But if we bring it over, we get back 1 plus wy to the p is congruent to w times z to the p mod q. But what do we have now? We have consecutive p power residues. And so in particular, so since wy and wz are reduced residues, I realized I wrote multiplicative residues when I should have written reduced residues. So since Wy and Wz are reduced residues, modulo Q, we have that Wy and Wz are non-zero, modulo Q. And therefore, Wy to the p and Wz to the p are consecutive p-power residues modulo Q. So therefore, we have that Wy to the p and Wz to the p are consecutive p-power residues modulo Q. A contradiction, since Q is an auxiliary prime for P. And the key thing is, we're looking at this equation right here. We have 1, so we have Wy to the P, that's a p-power residue. Wz to the P, that's a p-power residue. They are both non-zero, Wz and Wy, but Wz to the P is simply Wy to the P, that p-power residue plus 1. So we do get back consecutive p-power residues. But Q is an auxiliary prime for P, so we get a contradiction about that statement. And so we have this here. And so because we have a contradiction, that establishes our claim. That tells us that then Q has to divide X, Y, or Z. And so we have this division here. But we know that X, Y, and Z are relatively prime. So we have that they're relatively prime. So then by Euclid's lemma, Q has to divide exactly one of them. That Q divides exactly one of X, Y, or Z. And now what we are going to do is do a relabeling. So relabeling if necessary. Assume that Q divides Z. So here is a summary of what we have shown. We have that x plus y is equal to a to the p, z minus y is equal to b to the p, and similarly z minus x is equal to c to the p. And then the secondary factors, we showed that that was equal to r to the p, s to the p, and a t to the p, where a, b, c, r, s, t, these are all natural numbers. We just showed that q divides z after relabeling. So let us now go ahead and consider a to the p plus b to the p equals c plus c to the p. So observe that a to the p plus b to the p plus c to the p is equal to x plus y plus z minus y plus z minus x, which this here simplifies. We have that the x's cancel, the y's cancel, and we're just left with a 2z. But now, z is congruent to 0 mod q. So thus, we have that a to the p plus b to the p plus c to the p is congruent to 0 mod q. But we are back to where we started. Because if we come back over here, we have x to the p plus y to the p minus z to the p is congruent to 0 mod q. And if we run the same argument that we just did, where we said q divides x, y, or z, and now say, let's claim that q divides a, b, or c, and do the same exact argument, we go by contradiction, q does not divide a, b, c, and then do the same exact argument. That is going to show that that gives us a contradiction, and therefore q has to divide a, b, or c. So the argument just given then shows that q divides one of a, b, or c. And what we are going to do now is show that this is impossible by considering each case separately. And this will be our desired contradiction. So we're going to consider each case separately. So case 1, we're going to go ahead and suppose that q divides b. If q divides b, we come back to this equation here. So we have z minus y is equal to b to the p. Then z minus b to the p is equal to y. And since q divides since q divides z, we have, by the linear combination lemma, that q divides y. But now we are in trouble, because y and z are relatively prime. So this contradicts the GCD of z and y being 1. A similar argument shows that the same thing will happen if we do q divides z. So if we take q divides z, then we come up here, we have z minus x is equal to z to the p. So then we have x is equal to z minus c to the p, and once again, by linear combination lemma, we get that since q divides z and z to the p, we have that q divides x, which contradicts the GCD of x and z being equal to 1. And so it remains to check the last case, case 3. So we're going to now suppose that q divides a. Then we come up here, x plus y is equal to a to the p. So we have that a to the p, which is equal to x plus y. This is going to be congruent to 0 mod q. But if that's congruent to 0 mod q, that tells us that y is congruent to negative x modulo q. So using this, and the fact that we know that z is congruent to 0 mod q, so q divides z, so So we observe that we get the following. We're going to look at r to the p, and we're going to be looking at t to the p. And so we have those expressions up here. R to the p is equal to this, and then t to the p is equal to this. So here are the expressions. Now just copy it over. Now let's focus on the left-hand side. We have r to the p is equal to this. We're going to use the fact that y is congruent to negative x mod q. And so we're going to reduce modulo q. We're going to have x to the p minus 1 minus x to the p minus 2 times y, which is now negative x, which gives us x to the p minus 1. Then we're going to continue on in that manner. And just as before, we're going to have, oops, there's a y missing over here. So when we get over here to this step, we're going to have a negative x to the p minus 2 times y. That's going to give us back a positive x to the p minus 1. And finally, y to the p minus 1, but p minus 1 is even. Plug in y, negative x, we're going to get another x to the p minus 1. So we get back p copies of x to the p minus 1 modulo q. So this is just going to be p times x to the p minus 1 modulo q. Now let's look at t to the p. T to the p is going to be this here, but we are assuming that q divides z. So upon reducing modulo q, this is 0, that is 0, everything in between is 0, this is 0, and we're just left with x to the p minus 1. And so we get this here. But now t to the p is congruent to x to the p minus 1 modulo q. So consequently, we get that r to the p, which is congruent to p to the x to the p minus 1 modulo q, upon replacing x to the p minus 1 with t to the p, we get that this is equal to t to p times t to the p modulo q. And we claim that q does not divide t. So we're going to do this once more by contradiction. So let us suppose that q divides t. But now, if q divides t, we are in trouble, because then that would imply that q divides x. So then, q divides x. Because our t to the p is congruent to x to the p minus 1. So if q divides t, then this x to the p minus 1 has to be congruent to 0 mod q, and consequently x is congruent to 0 mod q. And so here we have a contradiction. So this contradicts the GCD of x and z being equal to 1. So q does not divide t, as claimed. So that means that that means that t is a reduced residue modulo q. So that means that there exists some natural number m such that t times m is congruent to 1 modulo q. And now let us consider the equation that we have over here. R to the p is congruent to p to the times t to the p mod q. We're going to multiply this equation by m to the p. So then we have that our equation, r to the p congruent to p times t to the p, t to the p mod q implies that r m to the p is congruent to p times m t to the p mod q, but mt is congruent to 1, so this is going to be congruent to p mod q. But why is this a problem? Well, we have on the left hand side a perfect p power, a p power residue modulo q. And so p is a perfect p power mod q. So consequently, we have that p is a p power residue modulo q. But this contradicts our assumption. That q is an auxiliary prime for p. Because by definition of auxiliary prime, we have that p cannot be a p power residue modulo q. We have just contradicted this. And that is our desired contradiction. And so this completes the proof. And we are done. We have proven Germain's theorem. And as we will see in our next lesson, this would lead Ernst Kummer to lay the foundations for algebraic number theory. Sophie Germain, the trick in her work is that she was able to bypass having to need unique factorization by instead focusing on the whole quantity over here. So, and that was the marvelous trick in her argument, is that rather than show that all the factors in the quantity that we have over here, that these are all relatively prime when working over the integers that join p fruits of unity. Instead, by using the property of auxiliary primes, she was able to go about her proof by just showing that x plus y and this here will be relatively prime so long as that assumption that we have in auxiliary prime held. And this allowed her to prove the first case of Fermat's theorem. 2 years later, independently, Dirichlet and Legendre, building on her work, proved the n equals 5 case of Fermat's theorem. So in our next lesson, we are going to continue our discussion. We're going to see the drama that unfolded in 1847 at the Paris Academy of Science with Gabriel Lemay, and talk about Kummer's proof and how that led years later to the foundations of ring theory, which we have been using throughout our course. We've been using rings to talk about the integers modulo n. And so we'll talk about that further in our next lesson.